Oh, one last time for Alessio. That's it. You're on your way home. So we have a banked corner. For a banked corner, I tend to dulp. So I'm going to draw the banked corner kind of looking like that. It says theta is 26 degrees. And there's the car. I'm not going to draw a car. What's the speed limit? We need to do a free body diagram. What are the forces acting on this object? Get the obvious one. I have gravity down. Normally, I would go components, but because the circle that I'm tracing out is horizontal, I don't want to go components. I want to add the normal force, which would be at right angles to the surface. I agree. Those are the two forces. The nice thing about a banked corner is if you're doing the posted speed limit, you don't need to rely on friction to make it around the corner. You can do it if it's icy or if it's good traction, doesn't matter. What we said here was our best strategy was to add these two together by drawing them tip to tail. Tell me when to stop. How do I know I have to stop there? Because I actually know what these two forces add to. It is winner minus loser, except it's vector math, so it's going to be a triangle. But when I add them together, I know the resultant is a horizontal force pushing me toward the center. And we did color, 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 color. We noticed that this here was where the theta ended up. They want the speed limit. I could maybe figure this out. Could I figure this out from the normal force? I'd have to play around with it. I tend to, since I almost always know gravity, I tend to use these two, opposite, adjacent. I'm going to use tangent. I get tan theta equals the circular force divided by gravity. Then I usually get FC by itself. FC is either going to be m4 pi squared r over t squared or mv squared over r. Which one am I going to use for acceleration? Did this question give me or mention speed, or did this question give me or mention period? Okay, sorry? So I'm going to go mg, tan theta equals mv squared over r. What happens to the masses? Well, that's good because they didn't give me a mass in the question anyhow. And they wanted me to find the speed. So as far as I'm concerned, I can either give you the radius and say find the speed, or I can give you the speed and say find the radius, or for giggles, I could give you the speed and the radius and say find little g if we were on a different planet. Which, I don't know, I might do just because space. Anyways, they want the speed. So again, I'm going to get v equals, there's going to be a square root of GR, and I also have a tan theta in it. V is going to be the square root of 9.8, 75, tan 26 degrees. 9.8 times 75, tan 26 degrees. Do you get 3? Oh, square root. Jeez, that seems awfully fast. Yeah, faster than sound. You get 18.9? I'm just curious, what is that in kilometers per hour? Oh, I did that totally wrong. Divide by 36 times by 3.6, Mr. Dueck. Okay, 68. So this would be a fairly fast corner. Maybe this might be coming off of an on-ramp or an off-ramp for a freeway where you're going from 100 and starting to decelerate. Anyways, 18.9 meters per second. If you got that, I would give you 7 out of 7. Otherwise, for 7 marks, what would I do? I would probably give you 1 mark if I saw the vector triangle. I would give you 2, 3, 4, 5, 6, 7, something like that. What else could I do with this? I could turn this into a using principles of physics right to explain. If you want to go twice as fast, does the radius have to be twice as big or 4 times as big? Oh, okay. Because of the squared, or I don't know. That's the only thing interesting that I can come up with here. Next page. We made an argument that this, the conical pendulum, is really the same as the banked corner. Chelsea, did you get it? Do you have a quiz or not? Okay, I'm making sure I'd given you one. I couldn't remember. So we have free body diagram, mg. In this case, it's tension going up. And again, although it's going up at an angle, Matt, I'm not going to go components because the circle that I'm tracing out is dead horizontal. Instead, I'm going to add these together. How? Tip to tail. I'm going to get a triangle that looks like this. I always draw the easiest one first, which in this case is gravity. Tell me when to stop. Right there. And that's going to give me, thank you, an FC. I also notice that theta is between a vertical line and tension. Theta is between a vertical line and tension. So that's going to make this opposite, adjacent, hypotenuse. This question here, they said find the tension in the rope. I think I'm going to use cosine. So I'm going to go cos theta equals mg over tension. That's tension, not period. I think I'm going to get the t by itself. That's going to be mg over cos theta. It's going to be 2.3 times 9.8 over cos 18. And I get a tension 2.3 times 9.8 divided by cos 18. I get 23.7, almost exactly. And that's a force, so newtons. If you got that, 3 out of 3. Otherwise, I would probably give you 1 mark for that, 1 mark for that, half mark for the numbers, and a half mark for the answer. Then they also would like me to find the centripetal speed. I think there I'm going to use these two. I probably could do this with tangent as well, but I'm going to use these two because I'm going to use stuff they gave me. I'm going to use tangent. Equals FC over mg. And Matt, I want you to notice that if I didn't need to do that. If I look at the previous question, I also had tangent equals FC over mg. This is why I'm arguing, Ben, this is really identical. In fact, now I'm going to do exactly the same thing. I'm going to go mg tan theta equals mv squared over r. The m cancels. If you've been on the Wave Swinger, the musical swings at Playland, you will notice that empty cars and full cars, they swing out to the same angle because the mass does cancel. There's a tiny bit of a difference because a full car has a little bit of air resistance, and we're ignoring that in our free body diagram, so fair enough. They want the speed. Holy smokes, again, I get V equals the square root of g tan theta. It's going to be the square root of 9.8 times r, 1.6 tan, what was theta? 18. Don't forget to square root this time, Mr. Dueck. 9.8 times 1.6 tan 18, square root. And I get 2.26, if I round up properly. I would take 2.25, but 2.26 meters per second. If you got that right, 3 out of, is this 3 marks? 4 marks. 4 out of 4. Otherwise, I would probably go 1 mark for that, 1 mark for that, 1 mark for that, half mark for the numbers, half mark for the answer. Then I would turn the page. Ooh, boy. This one had some teeth. So they want the normal force at location B. Well, free-body diagram, I'm going to have gravity and normal force. Who's winning? They both are. Who's losing? No one. I'm going to get this. mg plus the normal force is what's pushing me in a circle. And then I thought, I'm pretty sure I'm going to use v squared over r, and I'll convince you of that in a second. So the normal force is going to be mv squared over r minus mg. Do I know the mass? 320. Do I know r? 7. I don't know v. I'm going to have to figure out the speed. Is there a change in height? Is there a change in speed? Is there a yucky curvy path? This is a job for conservation of energy. So I'm going to go KE, from rest. It's just going to be PE initial equals, well, I got a couple of options. I could let that be the ground. If I let that be the ground, what height am I dropping this from? Well, how high is the actual hill? What does it say? How high is the actual hill? What does it say? It says this whole thing is 20. The radius is 7, so this whole thing is 14. I could let h be 6 and let my final potential energy be 0. Anybody do that? So I got to do this the long way. Fine. Potential energy final plus kinetic energy final. mgh initial equals mgh final plus a half mv final squared. Little kids and grown-ups can go on the ride. Times by 2, times by 2, times by 2. And I get this. 2gh initial minus 2gh final. That equals vf squared. How do I get rid of this? Oh, well, you know, I could leave it like that and plug this whole thing right into there. It's going to be a little yucky, but I think I'll do that just for fun. So I'm going to get this. The normal force equals m bracket 2gh initial minus 2gh final all over r minus mg. Now it's plug and chug. The normal force is going to be m, 320. Two times 9.8 times 20 minus 2 times 9.8 times 14 all over 7 minus 320 times 9.8. This is a fraction bracket. 320, another bracket. 2 times 9.8 times 20, take away 2 times 9.8 times 14. Close off that inner bracket, close off the top, divided by 7, and then minus 320 times 9.8. I think that's right. Y'all get 2,240? No? Yes? A few of you? It is right, pretty sure. So, pardon me? No, I think I did this earlier, and that's the answer I recall as well, using the shortcut method of just saying, why don't I let the height be 6 meters, let the final height be 0, because it's a lot less writing. Just saying. See, I did this. Bracket 320 times 2 times 9.8 times 6, close bracket, divided by 7, minus 320 times 9.8. And lo and behold, you get the same answer with a lot less typing. If you got that right, 6 out of 6. Otherwise, how would I give out part marks? Probably give out 1 for that. 1 for that. That's 2, 3. Probably give you 4 if I somehow saw an expression for V. Then it would be 5, half mark for the numbers, half mark for the answer. Yeah, I'm pretty sure you did. The real question then for B, for 1 mark, how many G's are they experiencing? Well, we know this. The normal force is 2,240. So the first thing I'm going to do is figure out the acceleration. That's going to be 2,240 divided by 320. They're accelerating at exactly 7 meters per second squared. How many G's is that? Once I have an acceleration, how do I convert that to G's? And by the way, what is 1 G? 9.8. Are they pulling a whole G? It's going to be less than 9.8. These people are going to feel lighter at the top, not heavier at the top. They'll be screaming in terror, but it's probably still safe. 0.714 Gs. 0.714 Gs. I would give you probably a half mark if you would clued in to find the acceleration, and then a half mark for the answer. Is that okay? Now we're going to repeat that for the bottom. And what we're really assuming is that at the bottom, we're just hitting the loop. So I'm imagining kind of this right here. What are the forces acting on it? We have gravity down, but FC is going to be winning. I'm going to have FC, sorry, not what am I putting FC on there? Normal force is going to be winning. Wow, Mr. Dueck, FC doesn't show up on the Freebody diagram. Shut up. I'm going to have normal force minus mg equals mv squared over r. The normal force is going to be mv squared over r plus mg. Because we're just starting to hit the loop, so what path are we tracing? We're just hitting the loop. Or just coming out of the loop. Okay? So, I need to find V. That's going to be done with conservation of energy. But since we're on the bottom, I think we can say all of the initial potential turns into all of the final kinetic. Because our initial kinetic, it does say from rest, and at the bottom, our potential is 0. So I'm going to get mgh initial equals a half mv final squared. And I'm going to get that v final is squared is 2gh initial. I'm just going to plug that in over here. I'm going to get a normal force of m 2gh initial. No need to square it because that is v squared, divided by r plus mg. The normal force is going to be m, was it 320? 2, 9.8, was the initial height 20? Yep. R was 7 plus 320 times 9.8. 320 times 2 times 9.8 times 20 divided by 7 plus 320 times 9.8. You get 21,056, or have I made a typo here? I'm good. Way bigger normal force at the bottom. So if you got that, 6 out of 6. Otherwise, I would probably go something like this. 1 mark for that, 1 mark for that, 1 mark for that, 1 mark for that, 1 mark for the number, 1 mark for the answer. Probably something like that. How did I know what? Brandon, what's your question?
How did you know it's going up if the A is like
Well, or it's coming down. It's right at the bottom. Here's what I'm arguing. Right there, you're still in a circle. That's my argument.
the A wasn't written there? Outside the circle. I know it's wrong.
No, you know what? You've got a valid point. I need to move that A. Good point. So I'll have to fix that with, or draw an arrow pointing right to there. Because your argument is, since A is far away from the loop, you said mg equals the normal force, and you just said it's going to be equal to m. You know what? I will accept that, but I'll also say, please make sure you can handle doing it this way, because I'll move the A if I give you this. But oh, sorry. I will not give you a question this long on the test that combines both conservation of energy and the loop. I'll give you enough that you can just analyze the loop without having to do all the conservation of energy. Is that okay, Owen? Good? You're not foolishly looking at your phone or anything like that? That would be silly in the extreme. Okay. How many G's? So again, I'm going to first of all find the acceleration. Also, I know the answer is going to be bigger than 6, because 6 G's was if we barely made it through the loop and we had some room to spare. It's going to be F over M, so it's going to be 21,056 divided by 320. And I get 65.8 meters per second squared. And now, if I divide by 9.8, I get 6.7 Gs. So this question is longer and tougher than I'm going to ask on the written. And I got to be honest, Chad, I don't even think I threw one like this on the multiple choice. It's just too long. It's just too long. Can you give yourself a lovely score at the top of the page, please, out of 28? Mr. Dueck, what, Brendan? We have our test next class. I'm going to pause the video.